All right, so let's go ahead and get started. Hope you had a nice break yesterday. Today we're going to continue on what we were talking about last time, which is thermal circuits. So just as a reminder, we're sort of still within the confines of talking about the benefits of miniaturization. And we just are taking time to mathematically derive some of those benefits directly for you. And one of the big things we're looking at are thermal time constants and how much power it takes to bring something up to a much higher temperature, and how that power shrinks enormously if you just shrink the dimensions of your whole system. And this is sort of still talking about this within the context of chip-scale atomic clock, which I described in the last lecture. And so this is from the last lecture. This is sort of showing the physics package from a chip-scale atomic, well, not a chip-scale atomic clock, a small atomic clock. That's not quite what we call chip-scale. It's small because it's 3 centimeters by 3 centimeters by 3 centimeters. That is not MEMS. Okay, that's small, but it's not MEMS. MEMS starts getting down to the micron size. So you may have people go out. People are calling all sorts of things MEMS or nano and that sort of thing. This is not, although some people have attempted to call this, even though it's that big. Okay, so this is not. This is an example of a macroscopic physics package for an atomic clock. It is smaller than most of the physics packages being sold out there, though. Okay, so this is a smaller example than most, and so we're going to end up with a smaller power consumption and a faster time constant than usual. But, you know, this is how maybe you can aggressively scale an atomic clock physics package using machining technologies that are not micromachining. And so this was the example we're looking at last time. So just as a reminder, we have this cell, which is a box. It's all made of glass. It's hollowed out on the inside with this cylinder, and this cylinder contains then atomic vapors, in this case cesium. It could be rubidium too, that they make atomic clocks out of. The gas you want to be able to interrogate with a laser, so that's why we're showing the laser right there, but the laser's not doing anything for us. We're assuming that none of the laser energy is going into this glass cell, that it passes right through the whole thing. We're assuming that we are heating this cell, though, because in order for the cesium to be in a vapor state, which it has to be, we have to keep it at 80 degrees C at least. Okay? Otherwise, it'll solidify or liquefy, and we won't be able to use it as a resonant gas in a coherent state. So this little thing that I've drawn here, this squiggly line, is the heater. I'm trying to draw this such that it's in the very center of this cell. Okay, so I don't know how I can better help you picture this. So this is the top view of the cell. I guess the cell is really a square right now, so let me draw it more like a square. If that's the top view of your cell, then this heater wire is doing this. Okay, and it's making all these serpentine squiggles there because I'm trying to get as much wire, as much resistance as possible between this, because I'm going to send a current through this. Think of this like this, where I send in a current that I'll use to heat. That current will go through, but as it goes through that, it's going to joule heat this thing. Okay, so we're experiencing then joule heating from the heater that we have there. But the important thing is geometrically I have this thing right down the center of this. Okay? And so what we did last time was we equated this to an equivalent circuit. And I had a much more complicated equivalent circuit to start with, because what you do is you take each individual piece of this, including each individual foot, the single cell that you have there, and you equate that to an equivalent thermal mass and equivalent thermal resistance. And the reason why we're doing this at all is so that we can make the problem much more simple for us to analyze, right? And so what do we want to analyze? We want to figure out how much power it takes to get this up at a certain temperature, in this case 80 degrees C. We want to figure out how fast we can get it to that temperature from room temperature. Okay, and it turns out that in any system, whether it's a mechanical system like this, or if it's an electrical system like a transistor circuit or so, it's always easier to analyze these systems if you can just equate them to circuits. So equate them to resistors, capacitors, inductors if there were inductors in this. There's all sorts of other things too that we'll play around with later in the semester. So controlled sources like voltage-controlled current sources, transformers, all sorts of different elements that you have in circuits. You can equate any mechanical system, any chemical system, biological system or so to one of these types of circuits. We happen to do a lot of it in EE for transistor circuits, but we're trying to use it on this to make this an easier problem to analyze. And so I equated this to a circuit last time, and I reduced it to this. And so it all reduces to a very, very simple circuit where the total thermal resistance in this whole piece of hardware here turns out to be 1/2 the thermal resistance of a foot divided by 2 plus 1/2 the thermal resistance of the cell. Okay? And the thermal capacitance in here ends up being the thermal capacitance of the cell, and that's because the feet are so small compared to the cell. Their thermal capacitance is minuscule compared to the cell. They're more than 10 times smaller than the cell's thermal capacitance. And so when something is more than 10 times smaller, I'm just going to neglect it, okay, to make the problem a lot easier. And those neglects that I did turned a complicated circuit into just this. Okay, this is a very simple circuit. This is something everyone should have learned in their first circuits class. If I gave the input power a step response where I turned it on, turn on the power right there at T0, then what's going to happen is this thing is going to rise in temperature, and it's going to rise just like this RC circuit with a rise time dictated by the time constant of the RC circuit. And a temperature that's sort of predicted by how much power you're putting into this thermal resistance. So the temperature in the end, I should have it written down somewhere here, is just this. Okay, at least the delta temperature, the temperature above the surrounding temperature, which is the temperature of the chassis here. That's going to be T minus T0 is equal to the power that you're putting into this times that thermal resistance that we determined by looking at the geometry, applying some thermal physics, and coming up with a simple thermal circuit. Okay? Now, this is the far out, the wide view picture of this. We then started zooming in on this and doing some of the mechanics of this. So it's one thing for me to say, okay, there's a thermal capacitance and there's a thermal resistance, but in the end we have to calculate what those values are. So we proceeded here first to find the thermal capacitance of the cell. Okay, so we're directly finding this thing right here, CTH cell. And we did that by just following that expression that I gave last time for thermal capacitance. It's just density of the material that you're making the thing out of times the volume of the material times this thing called specific heat. And really in all of this density and specific heat, those are constants. Those are numbers that have been supplied to us. So volume is the only thing we have to calculate. That's simple geometry. We did that geometry last time where we took a square box. That's the volume in that square box. We subtract from that the hole that's been cut out of this, a cylindrical hole that contains the gas, and we lead to a volume of 20.7 cubic centimeters and a thermal capacitance by just plugging that volume into this expression of 25.9 joule per Kelvin. Okay, and that's where we left it last time. And so what I want to do is continue this time by getting the rest of the stuff we need in this picture, and the rest of the stuff means getting this thermal resistance. Okay, so let's go about getting that thermal resistance. And so find thermal resistance of the cell. Now you notice in my little equation here, I don't really need just the thermal resistance of the cell. I need the thermal resistance of the cell divided by 2. So I can go about getting that by getting the whole thermal resistance of the cell, or I can just get half of it. And it turns out it's a lot easier just to get half of it, so that's what I'm going to do. Okay, so I'm going to find thermal resistance of the cell divided by 2. All right, so how am I going to do this? Well, first I want to take a look at this cell. So let's go back, take a look at this thing. And so if I just look at a cross-section of this cell, it's going to look something like this. It's that with a hole cut out of it, sort of a circular hole in it. Okay, and I gave you dimensions for this last time. You could see them right there. This is 3 centimeters. That's 3 centimeters. And so the location of my heater in this thing is right here. That's my Joule heater that's running through this thing. So it's running out of the page in this cross-sectional diagram. And so how do I want to calculate the thermal resistance? Well, I'm interested in the thermal resistance from this heater to a foot, right? So one of the feet in this is going to tell me how much thermal resistance there is. So where's my foot? Well, there's a foot, and there's another foot. Okay, so I've got those feet. I've got 2 other feet in the back. Now, you may want me to be very exacting about this, and I could do that if I wanted to. Okay, so if I took a top view of this thing, say I took a top view of this thing again. Well, it's a square, so let me make it a square. So this is a side view. This is a top view. Okay, in the top view, I've got 4 feet, right? I got 1 here, I got 1 here, 1 here, and 1 here. And then I've got my little heater going through this thing like that. Okay, so I can split this problem into a couple of different ways, right? I could say, all right, let's take this heater and let's cut it in half. So this half of the heater is going to be a power source there. That half of the heater is going to have a power source there. Okay, and then I can say there's some thermal resistance from there to there. There's thermal resistance from there to there. And maybe thermal resistance from that power source to that. So I kind of divide this in half. I could do this, okay, but I'm not going to do it, right? Maybe I'd be more accurate if I do this, but I'm not going to do it in the interest of time, partially because I'm lazy, which is not a bad thing, right? There's such a thing as constructive laziness, and constructive laziness allows you to get to the answer much more quickly, and a lot of times that's much more important than getting the exact answer, right? A lot of times you just want a back of the envelope, even if that back of the envelope's a little bit wrong. Okay, even if it's a lot wrong, you learn a lot from a back of the envelope calculation, right? Usually a back of the envelope calculations give you an optimistic view of what will really occur, and so that when you come back and you do the very exact analysis, it's not as good as what you thought, right? But sometimes it's good to have that optimistic thing because then it forces you to do it, right? It forces you to go in and look at the problem more closely. And then when you find that the real answer is not as good as what you calculated, you start struggling and say, wait, I want that real answer, right? Then you start engineering the thing, and then you get back to that real answer. Okay, so back of the envelope calculations, approximations are very important, and you should learn to do this, especially for your research, right? If you could do an approximate calculation, you're much better off than if you're able to do the more exacting calculation, believe it or not, right? You should be able to do the exacting calculation at some point, but the approximation is more important. Okay, so what am I going to do? I'm not going to split this into 2 currents. I'm going to call this one current source like I did in the circuit from last time, right? And I'm just going to say that I want the resistance from this point to that point. Not electrical resistance, we're talking thermal resistance. Right, so this is my RTH of the cell over 2. Okay, that's what I want to do. Okay, so how am I going to go about doing that? Well, it's all geometry, it's all material. Where's the material, right? The heat's going to flow through the material. So the heat's going to want to go from this point, it's going to go through that point, it's going to go to that foot. It's actually going to go to both feet, right? Because I'm sort of, the way I'm looking at this thing is like this. If that was my top view, in one instance, new computer, I don't have my duplicate thing, so I'm, can't even grab that whole thing. Hold on a second. So here's what I'm really going to do. I'm going to say this whole thing here is just one long heating source. right? And I'm going to say I've got one resistance here and another resistance going that direction, and this resistance is going to that where there's 2 feet. So I've divided this into just this very simple, almost one-dimensional problem here. Okay? And that's how I want to attack this problem. It's all geometry. You could do it this way too if you want. Right? This is just going to take you longer, and I'm not sure the answer is going to be that much better. Okay, so we'll do this. This will take longer. It may be a little bit more accurate, but it's just going to take a little bit longer, and I don't want to do that now. Did you have a question?
Yeah. Why is it the thermal resistance over 2 instead of twice?
Yeah, I guess what I'm really trying to do is I'm saying that I'm doing this. Remember in the equivalent circuit from last time we had this?
Yeah.
This is where those thermal resistances over 2 came from. Right? So it's part of our equivalent circuit. That's why I'm calling it thermal resistance over 2. So to half the total thermal resistance that you go across the whole cell. Okay? And you notice I'm keeping everything towards the bottom here. I'm going to ignore a lot of the stuff at the top. Right? And that's because part of our assumption from the beginning was that there was vacuum everywhere around this. Right? So if there's vacuum everywhere around this, right, and I've got heat here, is the heat going to want to flow up to the vacuum? No. Right? Because this foot here is going to thermal ground. So this point right here, where my feet are, that's thermal ground. That's where the heat's going to want to flow. Okay? So let's now do the geometry of this problem. Yes?
Last time when we did a calculation for thermal resistance,
The cell and the foot? That's right. I'm going to do the foot later. So I'm doing the cell right now, and then we're going to do the foot right after this.
I'm confused because you have put here for calculation.
Oh, I'm sorry. No, I'm only looking at the cell resistance right now. Later on, I'm going to actually draw the little foot, and we're going to look at that geometry, and we're going to get that thermal resistance too. Okay? All right, so let's go ahead and get this thermal resistance. So how am I going to do this? Well, this is a pretty, look at that geometry. It's got curvature in it, that sort of thing. So we're going to have to do some kind of integration here. Okay, so we're going to have to take this geometry, go from this point here, and integrate across this whole thing to get it right across here. And that's going to get us a value for the amount of volume, at least, that we have there that this heat has to go through. No, we're not. Okay? We're not going to integrate anything here, right? We want to do this nice, quick, and dirty, right? We're going to just divide this thing up into little squares. Okay, I got one square right here. Oops, it's missing this point. So what? Okay, it's missing just a little bit there. I don't care. All right. Okay, it's going up here. Oh, you're missing all this stuff. So what? Okay, because, right, this is vacuum up here. If you're thinking of current, this is like current going into an open circuit. Right, so for heat, that's basically an open circuit. Okay, we see vacuum going up there. So the heat doesn't want to go up that direction, right? It wants to go this direction toward the foot. Okay, just like any circuit. So you really have to put your mindset into a circuit mindset. If you were calculating resistance from this point to that point, you would not include squares going up here. You can if you want. They're going to have a very small percentage change to your answer. They will change your answer. They'll change it a little bit. Okay, but it's not going to matter that much. All right? So for a quick and dirty type calculation, I'm just going to take these two boxes right here. And so let's take this box. Let's take box number 1 right here. It's not the color I wanted. I want this one. Okay, so how about that box 1? What does that box 1 really look like? Well, if we look at its dimensions, that, according to the dimensions I gave last time, is 0.5 centimeters. Okay, if the whole side here is 3 centimeters, and this dimension right here is 0.75 centimeters. And by the way, it's going to be the same one for this box too. This box will be another 0.75 centimeters. Okay. This, what am I going to do? I'm going to guesstimate that to be about a centimeter high. Okay. Oh, wait a minute. What if it's 1.5 centimeters? What if it's who cares, right? It's 1 centimeter. That's close enough to this answer that we're trying to get right here. So what I'm teaching you is how to be somewhat approximate about this here. All right, so we have box number 1. And box number 1, right, this is just a cross section. So it actually has, a lot of mass going into the board or into the screen right here. And so here's my box number 1, sort of with these dimensions. That's 0.5 centimeters. And it's going in a perspective view into the screen sort of like that, right? And this is 0.75 centimeters. This right here, right, how deep is that box that I'm playing with? Well, that's 3 centimeters. Okay, so now I have the dimensions of this box, and the heat actually is flowing in this direction, right? Heat flow is going that way, okay, across this, which means that this dimension is the length, right? And so what I'm trying to do is calculate the thermal resistance. I guess I'll say box 1 is what this is, right? That's just going to be the length of box 1 divided by K times that area, right? The length I know is this, 0.75 centimeters. I'm just going to call that 3/4 centimeters, right, times K. And now to get the area of this thing, that's going to be this 0.5 centimeters or 1/2 times 3. Okay, that's the thermal resistance of box number 1. Right, and so now I can do the same thing for box number 2. Box number 2 is the second box here. Where I write thermal resistance, box 2, L over K times A. Well, this is also 3/4 of a centimeter long. It has the same material, so the same K, same thermal conductivity. It is now 1 centimeter high and 3 centimeters deep still. Okay? So in the end, the thermal resistance across both of these things, which is the thermal resistance of the cell divided by 2, right? Because it is half. Actually, why am I doing this? I should be doing this. Okay, it is half the thermal resistance. It's this side of the cell, that thermal resistance. Okay, and so that now is just going to be the sum of these two thermal resistances. So R thermal box 1 plus R thermal box 2. That ends up being equal to, if you just sum these together, 3/8 1 over K. If you plug in values for this, (3/8) times 1 over 1.05, but then I have to multiply by 100 centimeters per meter to get the units correct, and this ends up being equal to 35.7. You write that so it's legible. Kelvin per watt. Okay, so that is half of the thermal resistance of the cell, and again, it's just a geometry problem. But we're making approximations to get that geometry. This is back of the envelope. If we want to be accurate about this later on, plug it into finite element, which you'll be playing with this semester, and let the finite element program get the exact answer for you. But for you, you want the back of the envelope. You want the quick solution to know whether this is a good direction or not to go in for your research, for example. All right, so we have the thermal resistance of half the thermal resistance of the cell, but we're not done yet. As was pointed out, we also need the thermal resistance of the feet. So let's go and do that now. So the thermal resistance of one of the feet here. And so what is the foot? The foot is really just a little cylinder. It's a short cylinder. And I don't know if I gave these dimensions before, but I'll give them now. This is 2 millimeters high. Okay, the foot, let's say, has a 2 millimeter radius. So that's the radius of a foot. And so obviously the things that we need are the length of this thing, and the length of this thing is going to be just this. That's the length. That's the amount of distance that the heat has to go across to get to ground, which is on this side where the foot is planted on the chassis in this case. This whole thing is still made of glass. And the area, right, we'll be very interested in the area here. That's going to be pi times r foot squared. Okay? And so, I guess that's L foot. So in the end, we can determine the thermal resistance of a foot fairly quickly. That's going to be L foot divided by K divided by the area of the foot. I guess I should put foot under that. And so L of the foot is 2 millimeters divided by K, still glass, so 1.05 a watt per meter Kelvin, times pi, times another 2 millimeters squared here. Of course, that 2 millimeter cancels with the square from that. And you can do the simple calculation. This ends up being 151.6 Kelvin per watt. Okay, so this foot has a lot more thermal resistance, if you look at this, than the cell. That makes a little bit of sense because the cell, right, it's got a lot of width, right? It's pretty short. It's just not that long compared to it is longer than the foot, but it's still very wide. So there's a lot of conduit for heat to head toward the feet there. Now, my calculation is a bit wrong because I didn't separate it out into these 4 quadrants here, right? I didn't do this problem. I just did that problem there. Okay, so it's a little bit off, but it's going to give us a pretty good ballpark, a type of answer there. And so I have the resistance of the foot. Do I need the capacitance of the foot? I can easily calculate the capacitance of the foot, but the foot is so small compared to the cell. Why do it? Right? It's a volume thing. The foot is going to have very little thermal capacitance. That's why we neglected it last time. So let's now just go to the final thing, right? So we can now get to the point where we can address this circuit right here. Okay, so I can now find the total thermal resistance that I need right here in this circuit here. So RTH is going to be equal to 1/2 of RTH of a foot divided by 2 plus thermal resistance of the cell divided by 2. Plugging in numbers, that's 1/2. So the foot was 151.6 divided by 2. The cell I already calculated divided by 2. So that's just going to be 35.7. And this whole thing then boils down to this thermal resistance in this problem is 55.8 Kelvin per watt. And so now we have the thermal resistance in this circuit. We have the thermal capacitance of the cell, which we got last time. We can now calculate all sorts of things about this problem. Okay, so the first thing let's do, let's find the power required to maintain that atomic clock temperature. I'll call T infinity equal to 80 degrees C in steady state operation of this clock. And so that from the equation that I put down before, right, just looking at the voltage difference or the temperature difference in this case, so T infinity minus T naught divided by the resistance, thermal resistance in this case. So just like any EE problem here, any simple EE problem, I have these numbers in. That ends up being 0.99 watts, which to me is 1 watt. Okay, so to keep this cell at 80 degrees C requires 1 watt of power. Okay, and we're pretty much, that's a ballpark figure. What's the actual answer going to be? It's going to be a little bit different from that, right? Maybe, well, I mean, somewhere close to that, but for all intents and purposes, it's 1 watt for us, right? All right, so next thing we want to do is how fast can we get it to temperature, so let's just find the time constant. Okay, well, we know the time constant, very simple formula. That's RTH times the thermal capacitance of the cell. And if you plug the numbers in for what we have, you end up with 24 minutes for this particular cell. Okay, so it's 24 minutes for tau. How long does it take for something to warm up? Well, in general, it takes about 3 time constants, so 3 tau, to reach steady state. Okay, like tau, right, gets you up to a certain amount, 60% or so. Then you have to wait a little longer for that thing to actually reach the steady state. And so if you're really interested in a stable system before you're using it, like a stable spectrum analyzer before you're using it, you got to wait 3 times that time constant to make sure that it's steadied out, right? There could be oscillations, too, in the problem. So you want those to go away. And so therefore, I guess I could say should wait 72 minutes before using this atomic clock. Okay? And that's pretty much it. So when they fire NIST F1 up, you know that big clock that they have in NIST? It takes a long time for that thing to become steady. Okay, we're talking weeks. Right? They fire it up, and they don't use the time on it until a very long time, right? They're not going to pick the time off in 1 minute and say, okay, that's the time. Right? They're going to wait for that thing to level out and steady out, and then they're going to start using the information from that clock. Okay? So just an example of how you can calculate this. Let's take a look at a few quick examples before we actually attack the micromechanical version of this thing. Just to give you a little bit of practice into how to model things on the micromechanical scale. So on the micromechanical scale, for reasons that we're going to discuss very soon, the types of shapes that we're looking at are not like this shape where we've got this box with feet on it. Right? That's the macroscopic way that things are done. In the micromechanical domain, you might have something like this, where you have some kind of wall or anchor, and then you have a platform that's suspended by a very thin cantilever here. Okay, so this is my T0. That's going to be my 25 degrees C, or whatever that temperature is. This is a support beam, and this is a plate. A lot of micromechanical things look like this. Okay, so say I take this thing. This is a top view, too, of the thing. It could be a side view too, but I'm calling it a top view. And so how are we going to supply heat to this? Well, one way you could supply heat, right? You could put a heater on this, but let's take a different case. Let's say we take a laser and we nail this thing with a laser beam. Okay? So that laser is now going, it's not going through this thing, it's being absorbed by the structure. So we'll assume that the properties are such that it absorbs the energy from the laser, and all of it. Right? How are you going to model this thing? So what's the equivalent circuit going to be for this, so that you can determine, okay, for given laser power, what's the temperature going to be on this thing? So how do we want to go about modeling this? In other words, what's the equivalent circuit? Okay, so we want to look at the different pieces of this. So one, we see this anchor right here that I'm calling ground. Right? So right away on this side, I've got ground. Okay? Then I've got this beam here. But this beam, we've already talked about what that beam is equal to. That beam, right, is basically one of these. Okay? This platform is also one of these. Okay? And its capacitor is grounded here. is it's sort of the temperature, the energy across the capacitor compared to ground, which is the T0 temperature. All right, so that makes it easy. I'm just going to draw in all of these things. So I'm going to have a resistor right here, a capacitor right here. These represent the beam. So this is going to be the thermal capacitance of the beam. This is going to be half of the thermal resistance of the beam. This is also half of the thermal resistance of the beam. And this is now going to be connected to the plate, which I'm going to draw this way because I have space to do it, but it's really the same thing. I'm going to have a thermal capacitance for the plate. I'm going to have thermal resistances for the plate divided by 2. Okay. Now I need to put my power source in. And of course, power in the equivalent circuit is modeled by a current source from ground. So there's my power there. And that's basically the laser power. Okay. So I just need to solve this circuit here to figure out what the temperature is, right? This is going to be T1, for example. Actually, if I want the temperature on the plate, it's going to be right here. That's the temperature of the plate relative to ground, which is T0. Okay, so I'm just going to use this simple circuit to model this whole thing, and that's going to tell me what the temperature is. If I ignore all the capacitors, it'll be steady state. If I include the capacitors with a time constant, it's going to be, then I'll get the time constant. Yes? You're right. I should have the power in the middle of the plate. That's true. If I'm...
Does the bottom just from the plate actually go?
Oh, you're right. Yeah. So this should be an open circuit right here. That's an open circuit right there. Okay? And so I guess where the power comes in is also a function of where the laser is. So this makes a good opportunity. If I took a laser and I hit it right here, then the power would be here. Okay, so that would be location dependent on this. And so to be consistent, let me do that. Okay? So now the power input is a function of location on this. Okay? So why am I screwing up this equivalent circuit? That's because what I'm trying to get to is much simpler than this. Right? What I'm going to do is start neglecting things like mad. Okay, so let's start neglecting. Right? What do you think? How do you think we can make this a much simpler circuit here? Take a look at the geometry of this. Look at the beam, look at the plate. The beam is much smaller than the plate, which means what is much smaller than the plates? Thermal capacitance is, right? And so you can neglect that thermal capacitance there. Okay? On the other hand, the plate is much smaller or much larger than the beam. So where does the beam dominate over the plate? In the resistance, right? And so you can knock out these two here, also neglect those two, to the point where this whole thing just boils down to the following circuit, where you just have the beam grounded there. That goes straight into the thermal capacitance of the plate, and the laser power comes straight into this. Okay? And this then becomes my T plate, and that's my T0. Okay? So that really is the equivalent circuit that you should be working with this. Right? Taking into account, the open circuits, the fact that those resistors are very small, the fact that the capacitors are very small. Usually when doing this problem, I would not draw out this complete circuit. I would just go straight from here to here. Right? Just recognizing that there's things that are very neglectable in this. So obviously this is a much faster circuit to work with, And when you're talking with circuits, speed is necessary, unfortunately, right? So if you're taking a midterm exam, doing something like that, there's going to be enough circuit problems on that if you're too slow, you will get nailed just because you're too slow. Okay, part of circuit design is being fast, and being fast is being able to approximate and being able to neglect the right things. Okay? All right, so that's one example here. Let's go to another example. Okay, so another example is maybe a more complicated structure. So something like this, and maybe two beams going to the structure itself, a big plate here, and then one beam on the other side, also anchored in some way. So that's my plate. Let me label my beams. That's beam 1, beam 2, beam 3. Okay? And so now I want to supply heat to this in a different way. Let's assume that all of this is in a conductive material. Okay, and let's apply a voltage right here that I'll call V heat. Okay, and let's put ground on this side. That's electrical ground and an electrical voltage. That's electrical. That's also an electrical ground. It also turns out that it's going to also be a temperature ground as well, a heat ground as well. Okay, so let me indicate that by saying this is T naught, 25 degrees C. Let's also call this T naught here on this side, 25 degrees C. So those are thermal ground on both sides of this problem. And all I'm doing is now putting a voltage across this. Well, if I put a voltage across this, what happens to this? What happens after I put a voltage across this? Current starts flowing, right? And we just saw from our little atomic clock example that when current flows through a resistance, there's Joule heating going on, right? There's an I squared R power that is generated that then is going to go into this structure, right? So by sending current through this, you are heating the thing, and this is one of the more interesting ways to heat up a micromechanical system, right? You just send current through it by putting a voltage across it. So the current going through this, which colors? Let's do it this way. So I can call that I1, I2, that's I3. Okay, there's also a current going through the plate, but I'm going to ignore it. Well, I'll tell you. I'll ask why I ignore it a little later on. But if I have this current I1 going through this right here, then there's a power going through that as well, or power being generated. That's going to be I1 squared times the electrical resistance of beam 1. And remember that little subscript E denotes electrical resistance. Okay, so now you have to do some bookkeeping here. You've got two types of resistance. You have an electrical problem where you're sending current down an electrical resistance, but you also know that there's another resistance associated with that beam, and that's thermal resistance. Okay, they're just related by different constants. One of them is using thermal conductivity, one of them is using electrical conductivity, but it's all very much the same concept. But you have to bookkeep which resistance is which here. Right? One of them is putting power in, the other one is dissipating that power. Okay? So now let's go ahead and make an equivalent circuit for this whole thing. What's that equivalent circuit going to look like? Well, I've got two beams here going to ground. Right? And I've got first my plate here. Right? So the plate, if I wanted to be complete, hint, I'm going to eliminate my completeness very soon, right? Can be modeled again by this T network of elements. So that's the thermal capacitance of the plate. And I'm going to have some thermal resistances for the plate. Okay. That plate now on the left side is going into two beams. I guess I've drawn them to look identical, but they don't have to be. All right, but these two beams are going to have equivalent circuits that look like this, going to ground. And likewise, on the other side, I've got one more beam going to ground. So same equivalent circuit. Okay? And so now, I've just identified that there's a power source associated with beam 1. And so I have to put that power source into this thing. So this power source is coming right here. And that's the power that I'll call P1. Let's put this on that side. That's equal to the current I1 squared times RE1. Okay, I've got another power that's going into beam 2. That's P2, I2 squared times RE of 2. I do have another power source going into my plate. And I've got another power source going into beam 3 that I'll call P3 I3 squared times RE3 squared. Okay? So I've got all these power sources now going into this. That's the beauty of sending an electrical current through this. It generates heat power in every single sector of this thing. And that amount of heat power is fully a function of the geometry that you've got. The way that this power gets dissipated, which creates the temperature contours on this structure, is also very much a function of geometry. Okay, but if I look at this, boy, this is not a fun problem to do, right? There's a lot of things in this. Right? You know what I'm going to do to all these things, right? I don't like lots of things, so I'm going to start eliminating these things. And so let's go ahead and do that. So first of all, each of these beams, if you look at the beams, right, just dimensionally, I didn't give you dimensions, but if you sort of think of dimensions according to what you're seeing here, these beams are much smaller, right, than that plate. That plate is dominating, and that's what you're going to see time and time again in many MEM structures. And so in that case, if the plate dominates, there's no need to include the thermal capacitance of the beams. Okay, in addition, just like we did last time, the plate has a lot of width, right? So its width to length ratio is not as big. So its length to width ratio is not as big as that of the beams, and so these guys I'm also going to neglect, right? And because the plate, right, it has this length to width ratio that isn't so big, it's also not going to be very resistive. And so the power, the heat that's being dissipated in the plate is going to be very little compared to that dissipated in the beams. So I'm also going to neglect that power source. Now, unfortunately, all the rest of this you will have to analyze. Okay? And it's going to be an analyze by superposition, pretty much. So to analyze this, and I won't do the whole analysis. And let me just say one. You know a couple things, right? You know that I3 is going to be equal to I1 plus I2 just by Kirchhoff's laws here, right? Those have to be that case. You know that the current I3, what's that going to be equal to? It's going to be the voltage that I put across this whole thing, right? There's only one current going through this whole thing, and that's I3 in the end, right? So I3 is going to be whatever voltage I put across this, which I called V heat, divided by the total electrical resistance. I guess I should, in my nomenclature, do this. Right? That's then going to be the current going through this. So you solve the electrical problem first, determine all the different resistors, solve the electrical problem first, get all the powers. then get all of the thermal values, create your thermal circuit, input those powers in the thermal circuit, and then you circuit analysis again to determine the temperature at each of the different locations to get the time constant and all of that. Okay? And I guess one last thing I want to say about that, the analysis here is at 3. Use superposition. Okay, that means handle one current source at a time. And add their contributions to get whatever you're looking for. Say it's T plate, which would be the temperature right here. Okay? So that's how you would attack this problem. This is very similar to one of your homework problems. So I'm not going to do anything detailed on this, but this is almost exactly your homework problem, except your homework problem has some interesting things, more interesting things going on than that. Yes? Oops, yeah, I've screwed those up. Should just be I squared. Anything else? Okay, thanks. All right, so that's basically a number of examples for this. Now let's attack that atomic clock system that we have. And since you've seen so many examples of this, you're probably getting bored of me doing all sorts of examples. So what I'm going to do now is just steal from another part of this lecture, and that is steal these two right here. Okay, this was the chip scale atomic clock version that we talked about last time. And so, right, you could see how it differs from the macroscopic version, right? Where in the macroscopic case, look, I've got these feet. I got this big box and feet on it, right? You find things like that everywhere, right? In fact, right, that thing, it's got feet, right? Everything has feet. This has feet, right, with wheels, right? But in MEMS, right, you sort of have feet, supports, but they don't have to be feet. They don't have to be little blobs that are holding this heavy object up. They can be very long tethers like you're seeing right here. Okay, so the first question that comes up, well, why is it in MEMS we can do that, whereas in the macroscopic world we can't do that? Right? You may think, well, in the macroscopic world we want the feet because they take up less space. Right? But that actually isn't entirely true. If I took that thing there, right, and I tried to suspend that by a long cantilever beam or some beam that's sort of meandering like this, you think it's going to stay up? No. What's going to happen, it's going to do this, right? It's going to droop. And it's not going to be as stable. And if I were using that thing to project, right, every time I write on that thing, it'll be going up and down, and you'll see a picture that goes up and down as I write, right? So you don't want to support the macroscopic thing that way. But on the MEM scale, somehow we can support it that way. Right? And you can keep going on with this on and on, right? Bugs, right? How come bugs, like spiders, right? They have this gigantic mass, right? You can look at a daddy long leg, right? Gigantic mass, and its legs are really thin. Right? How is it able to support itself that way? Right? Ants, how can they pick up such huge things? How can all of this, right? This all has to do with getting smaller. When you get smaller, the design can change in a big way because of the way things scale. So in this thing, we're going to take a look at this in a second. Let's first look at the thermal problem here, then address that idea that I just talked about here. So same thermal problem. I have a temperature T0 on the outside of this thing. This thing is being held up by these long, slender supports now, which you can do on the microscale. You have a physics package, which is now very small, 300 by 300 by 300 cubic microns, right? That is a MEM scale thing. You could see the heater there, the meandering thing on top of this. I'm drawing 4 supports for this. I guess I could even have just had 2 supports for this thing. But now your supports, right, now you're looking at very different values for everything. I can keep that there. But right, if my supports are 500 microns long, maybe 10 microns thick, 20 microns wide, and if my cell is 300 by 300 by 300 minus what I'm calling a box of open a hollow box, right? So minus that hollow portion there. We're now looking at a volume of 5 times 10 to the minus 12 cubic meters. Okay, extremely small compared to that macroscopic thing. And so you use the same equation for thermal capacitance, and you end up here. Hopefully I have the answer on the other side. Yes. You end up here with 6.3 times 10 to the minus 6 joule per Kelvin. Compare that to the 25.9 or so of the macroscopic cell. So shrinking things down gives you orders of magnitude. That's 10 to the minus 6 there, a change in values. Okay, the supports, right, they're very long. They're very, their cross-sectional area is very thin here. And I'm going to use a worse material for thermal isolation. Right? Before it was glass, this is now polysilicon. It's just a fact of what we're able to fabricate at the MEM scale in a certain process. But even if that's not as good, yeah, that's not as good. Before it was 1.05. Okay, we still get enormously larger thermal resistance here. This is 83,000 Kelvin per watt. Okay, and so if you plug all these numbers in and try to get the power required to maintain 80 degrees again, that's now 2.6 milliwatts of power. Okay, and the thermal time constant is on the order of 0.13 seconds. That means in less than a second, this thing is ready to go. Okay, just because it's tiny. And so those are the true powerful things about chip-scale atomic clock. That, the performance is not as good as a NIST F1 that takes, right, the week or so to warm up and stabilize, that you can't carry around. But the practical application is enormous. Right? At some point, you may be carrying around a chip-scale atomic clock. Okay, why would you need that? Well, I was telling you before, communications require extremely good timing. The better timing you can have, the better your communications. The fewer the dropped calls, the more people can communicate at a time. All sorts of things get much better once timing gets better, and this may make it possible right here. And this is all becoming possible because of these things here. Okay, performance from a clock standpoint is less than the NIST F1, but performance from more important things like size, power, and speed to stability is much, much better, many orders of magnitude. Okay, so let's get back to that thing that I was talking about. How is it that we can support this thing with such small, thin supports here? Okay, so what makes all this possible? So all of this is due to scaling, I'm saying here. So I want to ask this question. What makes this all possible? Well, I just said there, it's all due to scaling. But can we mathematically show that? And so one of the things that scaling does that we already see, right, is that scaling reduces the thermal capacitance. Right? The thermal capacitance goes as a length dimension cubed, which means it goes as S cubed. If I make S go down, right? So if S goes down, then thermal capacitance goes down in a hurry, right? By the cube power right there. So that's part of it. Just a little bit of dimensional scaling starts making that thermal capacitance take a dive, and a very fast dive. The second thing that we're seeing here that I talked about here is that scaling, it allows the use of long, thin tethers. And these long, thin tethers then means that thermal resistance goes up. Because remember, resistance, whether it's thermal or electrical, goes up as the length of that material gets longer. Okay? And so what does this mean in the mechanical case? Basically, tethers, they can support more, which I'll put in quotes, when things are scaled. You can almost say they're getting stronger. Okay? So why is that? Okay, let's turn this over and take a look at that in more detail now. Let me take a little example here. Let's say that I have a mass, a square mass here that I'm going to draw right here. Just a block of some material. Okay, so there's a block of material that I have. Let's say that the material has dimensions. All dimensions are the same. It's a square. So LM there, and LM here, where the M is standing for mass. Right, so this is a block of mass there. Okay, let's say that we're going to do the MEMS thing. We're going to support this thing by a long beam. Right, so I'm going to take a beam, draw this beam out to here. It's going to, the beam's going to have a length, of course, which I'll call L sub B. It's going to have a width, W sub B, and it's going to have a thickness, H sub B. Okay, and I'm going to connect this to the wall. Okay, so how do I draw the wall? Well, maybe the wall looks like that. And this is all attached to that wall. Okay, so anytime that I'm supporting something like this with this beam, there's going to be a chance that that beam is going to droop, right? And so I could kind of measure that droop by, say, this X here, right? So let's say that that X is the droop. Of the beam. Okay, so that beam is there and it's going like that, right? Because the mass is too heavy for it. And so in order to model that whole thing, I want to model the droop of that beam. Let me say a few things about this beam first. First of all, the droop is going to be governed by the stiffness of the beam. So let's just say that K is the stiffness. But this beam is going to have a different stiffness along its whole length. We'll learn more about that later on in the class. But let me just say, to be correct about this, that this is the stiffness at this point right here where it attaches to the block, the mass. Okay, and that stiffness is going to be given by the equation which we will derive later on, 1/4 times Young's modulus, which you've seen before, times the width of the beam, times the thickness of the beam cubed, divided by the length of the beam cubed. And that's it. Okay? And so I should say this is a stiffness in the Z direction. Sorry, X direction, since I called that X. I called the downward direction X in this. Okay? All right, so what can we say about this? Why don't we look at stiffness first of all? Okay, what if we start scaling all the dimensions in this stiffness? So you know how to play the scaling game, right? That says this, there's a WB that scales by S. There's my HB, it scales by S cubed. There's my LB, scales by S cubed. This ends up going as S. Okay, so what does that tell us? That tells us that if I make S smaller, if I'm scaling everything, then my stiffness is going to get smaller. Okay? And that's not good, right? I mean, basically I was trying to claim that when you make things smaller, you droop less. Right? But in this case, we're seeing the stiffness get smaller. Okay, but there's another side to this whole thing, and that is the mass of this thing. Right? So this whole thing here has a mass. So M is going to be our mass, and that mass is going to be equal to what? It's going to be equal to the density times the volume of this thing. Well, the volume of this thing is just Lm cubed. Okay? And so this actually, right, if we want to do our scaling thing, that goes as S cubed. And so that says that as S goes down, mass goes down in a hurry. Okay, so stiffness goes down as you scale things down, but so does mass, and mass goes down a lot faster. Okay, so what's more important in the droop of this whole thing? Well, we can write an expression down for static equilibrium to get the droop. So at static equilibrium, I'm going to have a force acting on the mass due to gravity. Okay, and that's going to be equal to the restoring force applied by the spring. Okay, so in the end, I'm going to have something like this. Right, I have this force here, which is going to be mass times acceleration, where g is the acceleration due to gravity. And that's going to be equated to what the spring is exerting on this, which is kx in the upward direction. Okay, so I can just write mg equals k times x. So g is the acceleration due to gravity. Okay, and there's my little equation there. So I can rearrange this equation. Let's do that on this side. And I can get an expression for x. So x is just going to be mg, or m divided by k, times g. Right? And so I know that as I scale m, right, with dimensions, if I'm scaling all dimensions, then m I said was going as s cubed, k is going as s. So that goes as s squared, right? Which means that as I scale s, the amount of displacement x, the amount of droop that I get, is going to become smaller. Okay? So let me do that in words. As dimensions scale, smaller, the droop, x, goes down. Okay, so that puts us, I mean, that's what we're talking about here. So we're talking about the fact that when I make things smaller, boy, if that thing was drooping before, it probably is drooping much less just because I made it smaller. Even though all of the ratio of dimensions, right, the initial ratio of the sides of the box to the length of the beam, that ratio is still the same. It's just that everything is a lot smaller, and because everything is a lot smaller, that beam effectively is a lot stronger. Okay, it can hold that thing up with much less droop. And so what we're particularly interested in is our thermal resistance. Okay, so let's go back to our thermal resistance. How does this impact thermal resistance? Well, thermal resistance, remember, that goes as the length divided by the width divided by the thickness. Okay, and we want to raise this thermal resistance. Okay? And so it's interesting to try to figure out, you know, if I maintain constant droop. So say I had a droop in the beginning at a certain dimension, and then I scale everything down. And I scale everything down, but also increase the length, increase the thermal resistance while scaling such that I maintain that droop. Okay? What happens to that thermal resistance? How fast is that thermal resistance going to get higher? Okay, so let's ask this question. How fast does RTH rise as dimensions go down for a constant droop x? Okay, so we can easily do that by just applying a few equations. So we could take this equation right here, right? And I'm going to do my little thing here, where I'm going to show up on this side right there. So take that equation and just write it out. Okay, so I have mass, which I know is rho times Lm cubed times g, equals my stiffness, 1/4 E times W sub B times H sub B cubed divided by L sub B cubed times x, right, where that x in all of this is constant, right, because I'm looking for constant droop here. Okay, now I'm going to rearrange this to find LB over WBHB, and you can see that they're both, all of these are on the left-hand side of this, so I'm just going to pull them to the right-half side and leave some of the HB and LBs on, pull them to the left-half side, leave some of the HB and LBs on the right-half side here. So this ends up being 1/4 Young's modulus times HB cubed divided by LB cubed. All of this times x, which is a constant in this case, times 1 over density times LM cubed times G. Okay? And so now my scaling analysis on this says that, sorry, that's not cubed anymore, that's squared. Because I took one of them and went to the other side. Okay, so HB squared over LB squared. Okay, so this now turns into S squared over S squared times 1 over S cubed, which means this whole thing, those cancel, goes as 1 over S cubed. And so what's this telling us? This is saying that as S goes down, this quantity LB over WB times HB goes down in a hurry, right? That's a third power, which means, it goes up in a hurry. That's the third power, which means that the thermal resistance goes up in a hurry for constant group. So that tells us what we've already figured out, that if we scale everything, all the dimensions for anything supported by these long meandering struts, we can raise our thermal resistance. It is scaling that allowed us to raise our thermal resistance, that allowed us then to reduce the power that we put into this system to keep it at a steady state temperature. Okay, and because of the thermal capacitance scaling as well, it allows us to lower our thermal time constant. Yes?
Could you tell us, how did you get the first equation on the left?
This one?
Yeah.
The top one?
Yeah.
Okay, so this is mass times acceleration. That's the same equation as this. Right, mass is density times Lm cubed. Okay? Is that what you meant? How about this part is stiffness here? Okay, so in the end, I can even write this in this. Right, that's mass, and this is stiffness. These are the two things that I wrote back here. So I wrote a mass equation right here, and I wrote a stiffness equation right there. I'm just using equations that I wrote. Okay? All right, so that's going to be what I say about scaling. There's almost an infinite more things that you can talk about with scaling. When you make it smaller, you're going to find that you can always boost performance in some area. Something may go wrong, okay, but performance boost in some other area, and that has been the art of MEMS forever, right? Nanotechnology is doing the same thing, right? So ICs have done it forever, right? But that's sort of what MEMS is about. Yes?
One of the benefits of scaling is that CTH
Yeah, so what you're seeing, that's the other part of the scaling thing, right? So CTH goes down faster than RTH goes up, is what's happening here, right? So it's the cube thing that CTH depends on, and the RTH doesn't depend on the cube, right? RTH depends on 1 over S, right? Whereas the thermal capacitance goes as S cubed. So there's a square law difference. As you shrink things down, thermal capacitance goes down much quicker than RTH goes up. So that's why your thermal time... Yeah, it drops very fast. Okay, so time?
Well, why in essence do you want RTH to go up?
You want RTH to go up because to maintain it at temperature. So there's one thing of getting to temperature, but there's the other one about how much power do you put in to get to temperature. Right? So it took 1 watt for that 3 centimeter by 3 centimeter cell physics package that I looked at. It took 1 milliwatt, 2 milliwatts or so for the tiny version. And so many orders of magnitude smaller power. So you end up winning in everything, right? It's one of the nicest scaling things that we find. Okay. All right, so that's the atomic clock argument here. I guess I lied when I said that's it for what I'm going to say about scaling, because there's one more application that I'm going to talk about. So we talked about this. You looked at that as well. One more application I want to talk about is micro gas analyzers. This is sensors. Okay, so one of the biggest things that MEMS is applied to is sensors, right? And that's why we have the Berkeley Sensor and Actuator Center, and we're basically doing MEMS research and nanoscale research to try to get better and better sensors. And I'm going to show you here what a better sensor really means. Okay, so I'm going to talk about micro gas analyzers. This was another program that I ran at DARPA at the time. And so it creates an interesting case. So before this program, there were all sorts of sensors out there, right? There's sensors everywhere around you. But the question is, how good is your sensor? Right? How do you define how good a sensor is? And so let me help you in that definition. So here's a conventional sensor. Say we're trying to sense gas, which is what this program was all about, right? Carbon monoxide, something else, right? You want to sense the presence of a gas. And under minute quantities, and also, right, usually that's not the only gas that's there. You've got all sorts of other gases that are floating around in space. Okay, so one way you can build a sensor to detect a gas is to just create a capacitor where the dielectric between the two plates is a gas-sensitive polymer. And so, for example, if you throw some gas at this thing, species A, then what happens is that polymer expands. As that polymer expands, you get a larger distance between those plates. You get a change in capacitance, right? And thus you've detected the presence of that gas, right? You're just detecting that presence, the change in capacitance, which you can do with an electronic circuit, right? This is a very simple sensor. A lot of sensors work this way, but this is what I would call a not too good sensor. I'm not going to say bad because there's people working on this. Right, I don't want to say that, but it's a not too good sensor. And the reason why is because what if I put a species B on this thing? Okay, if I put a species B on this thing, right, usually you try to select a polymer that is selective only to one gas, right, species A. But you can't really do that. That's the problem, right? Okay, it may be sensitive to species A 100 times more than it's sensitive to species B. But what if you're trying to detect a presence of species A 1,000 times smaller than species B? So the whole place is surrounded by species B. You're trying to get species A, but species B is coming in, and even though this isn't sensitive to species B, it's making this thing expand. It's giving you a signal. How do you know whether you've detected species A or species B? Okay? That's the real problem with sensors. Okay? And so this is where DARPA was putting all of its money into, and that's why I get a little bit peeved when I see sensor work that doesn't look at selectivity, okay, that's not paying attention to exactly what you're sensing, whether you can sense just that instead of sensing everything else. Okay, how do you solve this problem? One of the ways to solve this is to separate the two analytes before you sense. Okay, one way to do that for gases is to use a separation analyzer, a gas chromatic column here. So a gas chromatograph here. So you take species A and species B, you put them on one side of a very long column, and what's happened is these two species interact with the walls of the column. Okay, as they're interacting with the walls of the column, it's changing their velocities. They interact with the walls at different rates. And so by the time you get out of this column, species B is ahead of species A because it just moved faster. It interacted with the edges of the column in such a way that it moved faster than species A. So now they're separate. And now you can use this same sensor here to detect them one at a time. You've separated them in time. Okay? You temporarily separate the analysis. And in this way, you can now detect the presence of both. You can detect the presence of A, because you know how long it should take for species A to go through. So you're timing this, and you're detecting the presence of something at that time. Okay, it turns out this is one of the best ways to identify something. And if you really want to identify something in a mixture, this is probably the way you're going to have to do it from a gas standpoint. And if you want it, but the problem with this is these systems are too big, too slow, too power hungry, right? That's how you decide that a given project is good for MEMS. You find something that's already implemented, and you look at its size and you say, oh my God, it doesn't need to be that big. It doesn't need to consume that much power. And what if I apply my MEMS technology to that? And I shrink it down in size. And so this is the too big right here. So this is actually a portable gas chromatograph. This is something you can carry around in a suitcase. That's it compared to a computer. That's sort of looking at certain analytes in this. And this is what this program was going after here, this chip-scale gas chromatograph. And you could sort of see what it was able to do, right? The size went down by 20,000 times from this 40 cubic centimeters to 2 cubic centimeters. The sensitivity, right? Even the sensitivity got better. 1 part per billion down to 1 part per trillion. The analysis time, 15 minutes. You had to wait that long just to get a good analysis, 4 seconds. The energy consumption, 10,000 joules down to 1 joule. This is all happening strictly through scaling, making the thing smaller. Okay, we're out of time now, so I guess next time we'll continue and I'll show you how this is all done.